Welcome to our talk. Today I'll be presenting our work on global topology of 3D symmetric tensor fields. This is joint work with Shih-Hsuan and Professor Zhang. Tensor fields have many applications in scientific, engineering, and medical applications. Tensor field topology is becoming an increasingly important aspect of tensor field visualization. The topology of 3D symmetric tensor fields consists of degenerate curves and neutral surfaces, as shown for this O-ring dataset. In solid mechanics, the degenerate curves in the stress tensor field indicate the locations of uniaxial extension and compression, while the neutral surfaces correspond to pure shear. Existing work on tensor field topology has focused on extraction and the local analysis in the vicinity of topological features. However, these features do not live in isolation, and their interactions can provide critical information regarding the data. For example, neutral surfaces divide the domain into extension-dominant regions, also called linear regions, and compression-dominant regions, also called planar regions. Each region can have sophisticated geometry and topology due to its interaction with neighboring regions of the opposing dominant behavior. Similarly, a degenerate curve can form a loop and even a knot. Two degenerate curves can be linked. In this paper, we introduce a topological graph for 3D symmetric tensor fields. A node in the graph can be either a region of uniform linearity planarity or a degenerate curve. An edge can indicate a pair of adjacent regions, a degenerate curve being contained by a region, or two linked degenerate curves. We also compute additional properties of each node and edge, such as the Benny numbers of a region and the right number of a degenerate loop. This graph provides a global view of the topological features in the data, along with the intricate interactions among them, which can lead to additional insight. Our topological graphs can also be used to study the similarities and differences in two tensor fields, such as the examples shown here. The two simulation data have slightly different boundary conditions, and it is not obvious whether and where their topologies are different, based on traditional visualization techniques showing degenerate curves and neutral surfaces. However, with the topological graphs, we can observe that while the tensor fields have similar structures in their degenerate curves, they have different number of regions. The difference in the number of regions is a direct consequence of the difference in their boundary conditions. A degenerate point can be classified as either a wedge or a trisector as shown in the left column. However, most existing work on tensor field topology has largely focused on the linearity's planarity aspect. In this paper, we advocate the combination of the linearity planarity classification and the wedge trisector classification for physical interpretation of our data, which can provide additional insight. For example, with the differentiation between wedges and trisectors in the data in the middle column, the users can see where the material is pushed out, the blue trisector curve, and where the material runs into a dead end due to the boundary loads, the green wedge curve. Without differentiating wedges and trisectors, both degenerate curves are linear and thus visualized in green as shown in the right column. This makes it difficult to explain why there are two degenerate curves near the boundary. With the wedge trisector differentiation, additional observations can be made. For example, with slightly different boundary conditions, the two simulation datasets have rather different topology. Yet, when inspecting a cross-cutting plane, it can be observed that the difference between the number of wedges and the number of trisectors is 1 for both datasets. This observation mimics the Poincare-Hopper theorem for 2D tensor fields and can inspire further investigation. In this paper, we introduce the notion of topological graphs for 3D symmetric tensor fields. We also advocate the differentiation between wedges and trisectors. In addition, we provide theoretical analysis on degenerate loops, including their indexes. Finally, we provide a pipeline to construct topological graphs given a tensor field. There has been much work in the topological analysis of 3D symmetric tensor fields. Zhang and Peng were the first to point out that triple degenerate points are structurally unstable features. Instead, double degenerate points are structurally stable and form curves, i.e., degenerate curves. There have been several teams of researchers working on robust extraction of degenerate curves, including our own. In addition, Zhang and al. Introduced the wedge trisector classification of degenerate curves. Neutral surfaces were introduced by Palacios et al. Later, Roy et al. And Xu et al. Provided robust and seamless extraction algorithms for neutral surfaces. The notion of topological graphs have been introduced for 2D vector fields and 2D asymmetric tensor fields. In addition, Tao et al. Proposed the use of semantic flow graphs for vector fields. One of the most important concepts related to our analysis is the tensor mode. It has a range of -1 to 1. When it is 1, the tensor is a linear degenerate point. When -1, the tensor is a planar degenerate point. A neutral point corresponds to the zero mode. Mode surfaces are isosurfaces of the mode function. A degenerate point can be classified as a linear wedge, a linear trisector, a planar wedge, or a planar trisector. A degenerate point is a wedge if the projection of the tensor field onto the repeating plane has a wedge pattern. A trisector degenerate point can be defined in a similar fashion. We now provide more detail on the topological graph. We can consider connected regions formed by removing the neutral surfaces. Each such region is a union of either all positive mode surfaces or all negative mode surfaces. Thus, the region is dominated uniformly by either extension or compression. In our graph, such a region is represented as a node, colored green if linear, or orange if planar. A region can have sophisticated geometry and topology. We capture this with its volume and homology. In our setting, a region has 3 non-zero Bettian numbers, with B0 being 1. Thus, we compute B1 and B2 and show them inside the square in the graph corresponding to the region. B2 corresponds to the number of bubbles trapped in the region, with each bubble being a region of opposite linearity-planarity. B1 corresponds to the generators of all non-contractible loops in the region. An edge is added between 2 adjacent regions. Furthermore, if a region is contained by another, a rectangle is placed on the edge to highlight this containment relationship. Each degenerate curve is also marked as a node in the graph. A degenerate loop is given a ring-shaped glyph, while an open degenerate curve is represented by a half ring. A degenerate curve and its container region are connected by an edge in the graph. A degenerate loop has the right number visualized to indicate whether it forms or not. 2 linked degenerate loops are connected by an edge with their linking number written next to the edge. In addition, we consider the winding number of a loop free of degenerate points. Starting from a point on the loop and traveling along the loop once, the final tensor frame formed by the eigenvectors at the starting point can differ from the frame before the travel. The difference must be a rotation of 180 degrees around either the x-axis, the y-axis, or the z-axis, which correspond to quaternions I, J, and K respectively. We can see that the winding number is I for a linear wedge, or -y for a linear trisector. Similarly, the winding number is K for a planar wedge, or -k for a planar trisector. While the winding number is defined for non-degenerate curves, we can extend it to degenerate curves through tensor field continuity. For detail, please check out our paper. Thus, the winding number along the degenerate loop is well-defined and is referred to as the index of the degenerate loop. When the index of a degenerate loop is not 1 or -1, it must be linked to at least another degenerate curve. Our graph construction algorithm has 3 stages. In the first stage, we extract degenerate curves and neutral surfaces. Next, we identify the regions and determine their adjacency and containment relationships. Degenerate curves and their containing regions are also marked at this stage. In addition, we compute the volume of the Bettian numbers of each region. In the final stage, we determine the knots and links in the degenerate curves. Details of these steps are given in the paper. We apply our global topological analysis and wedge trisector differentiation to several applications. In the first application, we studied the stress tensor in an O-ring under various rotational symmetric and periodic load conditions. When the load is uniform as shown in the left column, we observe a single degenerate loop at the core of the O-ring, indicating extension dominant behavior as the uniform loads from the boundary reach an equilibrium there. However, when the boundary conditions become anisotropic, yet rotational symmetric and periodic, we observe a threefold symmetry in the contractile regions and the linking number of 3 between the two degenerate loops. Both match the threefold rotational symmetry in the boundary loads. In addition, the core of the O-ring has switched from extension dominant to being compression dominant, highlighting the increased load strength on the boundary. When the strength of the anisotropy further increases, a planar degenerate loop appears at the core, which is self-knotted with a right number of 3, again matching the rotational symmetry in the boundary loads. In all these cases, the shape of degenerate loops reflect the twists in the boundary load conditions. Please see our paper for additional application examples. To conclude, in this paper we introduced the notion of topological graphs for the global topological analysis of 3D symmetric tensor fields. We also provide an algorithm to construct such a graph given the tensor field. In addition, we provide analysis on the index of degenerate loops and advocate the differentiation between wedges and trisectors for physical interpretation. For future work, we would like to identify all potential bifurcations in 3D symmetric tensor fields, which can lead to a multi-scale visualization framework. We also plan to explore better layouts for our topological graphs. Finally, extending global topological analysis to 3D asymmetric tensor fields is the direction we wish to pursue. We would like to thank Peter Oliver for his help during video production. We appreciate the constructive feedback and suggestions by our anonymous reviewers. Our work was partially supported by the National Science Foundation. Thank you for your attention.